Hello once again, class, and welcome to another mock lecture. Today we're going to talk about the chain rule. To do this, I'm going to start doing some derivatives here that are going to increase in difficulty a little bit. So right now I'm going to play the role of basically a student that's trying to do some differentiation with what we know so far. So let's get to it. Alright, this one's pretty easy. You're just going to use the power rule on 2x squared, bringing down the 2, multiply by 2 to get 4, and then reduce the power by 1. The derivative of 25 is 0. Okay, no problem. All we're going to do is realize that when you square a binomial, you're multiplying it with itself. So I did that here, multiplying with itself. And now I'm using the power rule in two different locations, bringing down the 4 to get 16x to the third, and then it looks like we're going to get 200x for the next part. No problem. Okay, for this one, we are going to go ahead and we have to multiply this thing with itself 3 times. I mean, luckily we already know what's going on with this one. We've done that already. So then we just have to multiply this. That's a pretty big box method, but nothing we can't do. I'll just... Well, wait, I wasn't done with the last one. I mean, I can do this one. We just have to multiply this thing with itself 4 times. That's not really a big deal. Oh. So clearly what we need here is we need to find a way to differentiate something that looks like a composite function. Composite meaning it's a function that's inside of a bigger function. This is like 2x squared plus 25 that's plugged into, I don't know, maybe we'll call it u to the 100. So u is this 2x squared plus 25 thing. We need a way to be able to do this. And that's called the chain rule, right? And the way that we're going to do this differentiation is I'm going to just call this function y. To kind of set up what the chain rule is, I'm going to call this function y. What we need to find is dy dx, right? The derivative of this thing. So I'm going to let y be equal to u to the 100 power, where u is specifically the thing that's being raised to the 100. It's 2x squared plus 25 in this case. To find the derivative of this thing, I need to find the derivative of y with respect to u, and that's something that we can do, right? It looks like it's just going to be a power rule situation. And then I want to find the derivative of u with respect to x. So I'm going to find two different derivatives. I'm going to find dy du, that's what this one's going to be, derivative with respect to u, and this one's going to be du dx. Okay, I think I have that actually in the next slide. Here we go. Dy du is going to be, just with power rule, 100u to the 99, and du dx, the derivative of u with respect to x, is just power rule stuff. It's just 4x, and then this goes to 0 because it's a constant. But what we want is dy dx. We don't have that right now. We have dy du, and we have du dx. How are we supposed to find dy dx, which is what the derivative of this thing is? That's y prime. So the main question is, can we get dy dx from these two things here? And the answer is yes. Actually, you might even be able to see it by looking at their ratios. If you multiply them together, these things get linked. I drew a little chain. That's how I think about the chain rule. And so if you multiply dy du by du dx, the du's go away. It's like a conversion factor almost, and you're just going to be left with dy over dx. So in this case, we're just going to multiply 100 u to the 99 times 4x. U itself, though, is 2x squared plus 25, and so this is our derivative. You can make it look a little bit nicer by, multiplying the 4 with the 100, putting the x out in front, and that looks a lot nicer. And this is the thing that's modeling the slope for this. It is the true derivative. And that's the chain rule. It says let y be equal to a composite function. We're going to call it f of g of x. Now, you might have the notation be f of g, right? F composed with g of x. That's what this thing is. Where g of x is differentiable at x and f of x is differentiable at g of x, then the chain rule says that the derivative of this composite function is the derivative of the outer function times in terms of the inner function. Right? That's important. It's the derivative of the outer function in terms of the inner function times the derivative of the inner function. That's it. That's the chain rule. This allows us to differentiate composite functions. If you're going to let u be equal to g of x, which is a very common strategy, we could write the chain rule as dy dx is equal to d du of f of u, right? U being the inner function again, times du dx, or this is the way that we kind of came up with it. Dy dx is equal to dy du times du dx is what that should say. Du dx. Okay, because these things link and cancel, and so you get dy dx. So let's do some examples. Number one, let's let k of x be equal to the secant of x squared minus x. So it's a composite function. We're going to go ahead and let u be equal to x squared minus x. It's the inside piece here. And then I'm going to let f of u be equal to the secant of u. This we know how to differentiate. This we know how to differentiate. So let's do that. Du dx here, u prime, if you will, is 2x minus 1. And then du of f of u, the derivative of f of u with respect to u, is the secant of u tangent of u. That's just a trig derivative. Now we want to find k prime, right? This is the chain rule. It's du of f of u times du dx. The derivative of f with respect to u times the derivative of u with respect to x. So I'm just going to do that. I have, written this, but I've replaced the u with what it is in terms of x. It's x squared minus x. That's why instead of secant u tangent u, I have this, secant x squared minus x, tangent x squared minus x. And then I'm just going to multiply by du dx, 2x minus 1. And then I'm done. I rewrote it a little bit to make it look a little bit nicer, but that is the derivative. Example number 2, let's differentiate x squared plus 2 quantity cubed times x squared minus x plus 3 all raised to the 4th. Now this one is like, you do have to use the chain rule in each part, but the bigger kind of rule that we need to use for differentiation here is the product rule. And so that's what I did here. We've got something times something else. So first I just wrote the product rule. Got the derivative of the first function times the second function. I just realized I forgot a fourth here. Plus the derivative of the second function. Boy, that looks wonky. Times the first function. There we go, it fixed itself. For this first part, I still need the fourth there. For this first part, we need to use the chain rule to differentiate x squared plus 2 quantity cubed. So I'm going to go ahead and I'm going to let u be equal to x squared plus 2, the inner part. The outer function, and remember, we're just focusing here, okay? Just looking at that piece. The outer function is f of u, that's u cubed, which I differentiated to be 3u squared. And then the inner function has a derivative, du dx is 2x. So when I go to write this thing out, oh good, I put my 4 in there. When I go to write this thing out, we have 3 times x squared plus 2 quantity squared, right? That's this overall this thing, but instead of u, I'm putting in the x squared plus 2, and then multiplied by 2x. Okay, so this is the chain rule part. I'm still multiplying by this thing, and that's why this is here. The second part also requires chain rule. We have to take the derivative of x squared minus x plus 3 raised to the 4th, and then I'm going to worry about this later. I'm just going to tack that on at the end. So in this chain rule, I'm going to call it v, so there's no notational overlap, but I'm going to call the inner function x squared minus x plus 3. I differentiated that to be 2x minus 1 via power rule stuff. The outer function here would just be v to the 4th, because if that's all just v, you got v to the 4th, and by the power rule, that's v to the 3rd times 4. So plug in all this stuff in using the chain rule to kind of combine all this stuff. We have 4v cubed times the derivative of v. And then I still have the x squared plus 2 all raised to the 3rd. And then at this point, it's just a lot of algebra. I don't necessarily want to go through all this stuff. I mean, you have your derivative here. This is the derivative. It doesn't look nice. And so I kind of expanded some stuff. In this example, I multiplied the 4 with the 2x minus 1 to get 8x minus 4. Here, I just multiplied the 2x with the 3 to get me the 6x. And then I factored out this stuff, which gave me this left over. And then, I kind of I expanded all of this stuff to try to combine some like terms in here. And so I did end up with something that looks a little bit nicer, but our derivative, really happens here. That's where the derivative of this thing happens. And then everything after that is just a bunch of algebra to make it look nice. So I invite you to pause the video and follow along with what I did there. I do prefer this form down here. I think this looks way nicer, and it's actually even factored, which is also nice. But this video is about differentiation, not about algebra and changing the form stuff. So there you go. Now, the other thing that I want to get from this example is we can generalize the power rule. right here in this one, when we were differentiating x squared plus 2 all raised to the third power, I brought down the power, subtracted it by 1, and then multiplied by the derivative of the inside. In this one, right, again, brought down the power, subtracted by 1, that gave me this part here, and then I multiplied by the derivative of the inside. And that rule we're going to call the general power rule. If n is any real number and g of x is differentiable, then the derivative of g of x to the n, which is a specialized form of the chain rule, I'm going to bring down the power, subtract the power by 1, and then multiply by the derivative of whatever the inside function is. And I want to finish here with why this thing is even called the chain rule to begin with. Well, if you have a super composite function, like f of g of h of k of x, and the inner function is k, so I'm going to call that b. We're going to call a then h of b. We're going to call u g of a, so that y can be f of u. Each function is called something different. And we've linked them all together, right? In the sense that it's f of u, which is g of a, which is h of b, which is k of x. Okay, so they're all linked together. Well, if you multiply all these derivatives, right, with respect to whatever the variable that they're in terms of is, these things all pair up, right? It's like you're linking them all together with a type of chain, and they all cancel, and that's how you're going to get dy dx. My kind of concept image of, and here's another example, right? We're taking the derivative of the tangent of cosine of sine of 3x to the fourth plus 2x squared plus 1. My concept image is that of an onion. That's an onion. Pretend that looks like a much better onion. It kind of looks like a target, but it's an onion, okay? You just start peeling it away, right? We're just peeling out the outer layers. So the first thing I'm going to do actually is I'm going to take the derivative of tangent. Okay, then I'm going to take the derivative of cosine. Then I would take the derivative of sine next. That'd be the next layer, and the innermost layer would be the derivative of 3x to the fourth plus 2x squared plus 1. So in practice, here's what this looks like. When you're using a chain rule, this is a mega chain rule problem. It's a function in a function in a function in a function. But we're just going to peel away layers of this function until we've taken the derivative of the innermost layer. So I'm going to start with the derivative of tangent, which is secant squared. Now, on the inside here, I'm just putting what tangent is in terms of, right? You could call that thing u if you wanted to. So it's secant squared of u. But then you have to multiply by the derivative of u, of the inner function. Well, that also is a chain rule. So we're going to multiply by the derivative of cosine. The derivative of cosine is negative sine. And what is it in terms of? Well, it's in terms of, I think I called it a, right? So a is the inside here. So now we need to multiply by the derivative of a. The derivative of a, in this case, is cosine, right? So you have to take the derivative of the sine function. Now you have the cosine of its inner piece. I think we called it k or b. I think it was b. But the point is, we need to multiply by the derivative of its inner piece, right? If we're just looking here, we've peeled away everything. We're on the second most inner layer. We just took the derivative of that, and now you need to multiply by the derivative of that inside layer, which would be just power rule stuff, right? 12x cubed plus 4x is how you would get that. And that's it. We've kind of peeled this thing away until we've reached the innermost layer of this composite function, and then you just multiply by the derivative of that innermost function, and then we're done. That's how chain rule works. That's my concept image. And we could spend time making this look a little bit nicer, but again, at this point, it's just algebra. And to be fair, there's actually really not that much you could do, right? I think I would just move this negative out in front, and then I'd probably leave it all the same because I don't want to deal with simplifying that much more beyond this. And by the way, I should make a note. It's really easy to lose sight of what you're doing when you're doing a mega chain rule like this. So I always think it's important to remember, what did we just do? What is this? Well, it's a derivative. So this crazy looking thing models the slope for this function. All right. So that's it for this one. That's the chain rule. Hopefully you guys learned something. If you have any questions, please shoot me an email or leave a comment below. Thanks a ton for watching. And I'll see you in the next one.